Start with talking about water source heat pumps. Water source heat pump is a unitary type piece of equipment. It's packaged, compressor, fan, evaporator, condenser. They're water cooled compressors. Hence water source heat pumps. They're reverse cycle. In fact, I don't have that diagram drawn 100% correct. Reverse cycle meaning that you'll have to switch over, run your refrigerant through the condenser in the heating cycle, using the evaporator as the heat rejection source in lieu of the condenser. Units are available in vertical upflow units that sit on the floor, horizontal units mounted above the ceiling, counterflow applications just like residential furnaces. You get them in standard, high efficiencies, water source, and geothermal. Geothermal meaning that you're using the earth as the heat exchanger versus a cooling tower or a fluid cooler, and we'll get into a little bit more detail on that. Water source heat pumps also come in console units or floor-mounted fan coil shaped units, thin, 48 inches wide. There are some manufacturers that are making them in rooftop applications. I think there's a job out there on the street right now, or just did here a couple weeks ago, that had some rooftop applications. More and more manufacturers are getting into the reverse cycle package units. Another thing you can do with the water source heat pumps is the water chiller heater. We have one in our building. It's a reverse cycle chiller, meaning that we can make 45-degree water, or we can make 120 or 130 degree hot water. In our application in our building, we have a variable volume air handling unit with a water coil in it. In the wintertime, we make hot water with our chiller. We run it through the air handling unit. We preheat the air for the VAV system. We either heat it up to room neutral conditions or just slightly above room neutral conditions, and we let the VAV boxes with their perimeter heating take care of the actual building load. Summertime, we get cooling out of it. So it's kind of like a two-pipe air handling unit. We also have a storage tank that we run the water flow from the chiller through. So we use an economizer in those mild periods. For instance, when we start out in the morning needing heat, and we've made 120-degree water, during the day we'll eventually turn the chiller off, start running water through the storage tank, through the coil, and let the economizer neutralize the water temperature. Get it back down, and when in the afternoon you might actually need cooling. And so your water storage water is back down to 70 degrees. They also make domestic water and chiller heaters. You can buy them with dual wall heat exchangers. You can use the heat pump to make domestic water.
We can use that application, say, when geothermal has cold water in the wintertime, and that in the food.
I'm not following you.
Well, you know, a lot of times you have 30-something degree water in the winter if it's cold outside. Could you use something like that to warm the water up?
Oh, yeah. Yeah, you could use it to warm the water up.
Yeah.
Yeah.
For your other units?
Yeah. You could use it as a preheater for your loop.
Okay.
Heat pumps start out at probably half a ton to 3/4 ton. The package units are the horizontal and vertical units. I think the vertical units probably go up to like 7.5 to 10 tons, and the horizontal units might go on up to 20 tons. Most manufacturers. You can't even get a variable volume application in most manufacturers' heat pumps, meaning that you can add a drive to the fan. You inherently have a little bit of problems with variable volume in DX applications and getting oil return back to the compressors, so you have to be very careful in the minimum airflow that you go down to. You may not be able to turn that unit down to like 50%, but you can still do variable volume applications in the units, say 10 tons and above. They are constant air volume single zone for the most part, meaning that you've got one heat pump per zone. For instance, this room right here even though we've got a variable volume application in our building with an air handling unit, since this building is strictly interior and might need cooling in the wintertime, we put an individual heat pump in this room so that it's taking water off the loop. You can either heat or cool independently of anything else in the building. Humidity control using one manufacturer uses hot gas bypass from the compressor. They put a hot gas coil downstream of the evaporator, put a modulating or two-position valve on that hot gas so that they're sending hot gas right through the evaporator, or right through an evaporator coil downstream of the evaporator coil. One manufacturer uses hot water coil, and they take the hot water off the heat exchanger and run it through a coil for reheat. You can't get electric heat options. Most manufacturers, or most designers, don't put any additional heat in water source heat pumps. One of the problems, inherent problems with a geothermal system, in the wintertime you could be dealing with 39, 40 degree water. And your heat of absorption out of that water gets very minimal. So your capacity kind of drops. You know how air-cooled heat pumps drop at about 45 degrees. You don't get much capacity out of an air-cooled heat pump. Same thing happens with a geothermal heat pump when you have very low loop temperatures. You don't get much heat out of it, so consequently you have a very low delta T on your air. So you might be delivering 85 degree air to a space in the wintertime with a geothermal heat pump. That could cause a draft on some people. You don't have a very good air distribution system. So the reason for electric heat is to supplement that heat, because you can, with normal heat absorption, water temperatures, you can generate enough heat out of the compressor, but when your water temperature is very cold, your air delta T goes down. Domestic heat recovery, that's another little heat exchanger, refrigerant to water heat exchanger built into the heat pump, where you run your domestic water out of your storage tank, through the heat exchanger and back into your storage tank. You have to put a little separate circulating pump on your domestic water to draw it out of your storage tank and put it back in your storage tank. But then when the unit is on, it delivers hot gas to that heat exchanger so that you're actually getting a little bit more energy efficiency out of the heat pump. You're using that domestic water heat exchanger to absorb some of the heat in the system. EERs, most packaged air-cooled systems are in the 12 EER range, very high end. A water-cooled system, meaning that I'm operating at condensing water temperature, or condensing refrigerant temperatures, 110, 105 versus 120 to 125 for air-cooled system. So if I'm operating at a lower condensing temperature, my compressor lift is less, so my energy efficiency is naturally higher with a water-cooled unit versus an air-cooled unit. You have to consider it in a water-cooled system, there are several auxiliaries that you have to pay for and operate, like pumps and cooling towers. But the initial equipment of a water source heat pump can get up, even with a tower system using 85 degree or 90 degree water, it can be up as high as 16. Some geothermal systems where you have an adequately sized geothermal system and you're able to maintain maybe an 80 degree loop temperature, your EERs get up into the 20s, low 20s, 21. So it seems like something that people ought to be using, because the first cost is just only slightly above package systems in schools, generally 20 or 30% less than a typical VEV system with air-cooled or water-cooled chiller. But there's only still a couple engineers using water source heat pumps. You do have a water-cooled compressor, so your life of that compressor is extended, say, from 8 to 10 years to 12 to 15 years, because you're operating at lower condensing temperature. But you do have a compressor per unit. So wherever you set those units, you have a compressor to maintain. So I kind of shy away from horizontal units above ceilings, and interacting with people that are designing systems and try to put them in areas where they're more accessible. low first cost compared to other systems. I'm out of that business anymore, but most water-cooled systems, VAV, air handling units are running $5,000 a ton compared to $3,000 a ton maybe just 10 years ago. Water source heat pump systems with a evaporative condenser or fluid cooler or heat exchanger and coolant tower are generally running $3,000 to $3,500 a ton installed. Package split systems are up as high as over $2,000 to $2,500 a ton now compared to $1,200 to $1,500 a ton 10 years ago. So you can see that it's kind of priced right there in the middle with depending on what you utilize as your heat rejection and heat absorption equipment can be pretty high efficient compared to a central system when water cooled, air cooled chiller. Certainly an air cooled chiller it's equal. Low maintenance costs. There's not a lot of controls on a water source heat pump system. They're pretty well self-contained. You can use just standard 5-wire thermostats, or if you do want to monitor, you can put temperature controls on to be able to monitor and schedule in a front-end system. But the type motors that are used on fans are very high efficient, either ECM, electrically commutated motors at a variable speed, or single speed motors. So you got a fan motor, you got a compressor, and in the water source systems, most manufacturers only put distributors on the evaporator coil. In a geothermal system, they do put expansion valves, so there is some maintenance to an expansion valve occasionally. So compressor, fan motor, expansion valve, if you've got a geothermal system, that's about it. The heat exchangers, 99% of them aren't going to leak, or 99.9% of them aren't going to leak. You do have some manufacturing problems in evaporator coils occasionally, but generally that's just a bad run and is cyclical. The other maintenance includes your circulating pump for your tire water system and your tire water fan and any chemical treatment that you might have in your tire water, whether it's a fluid cooler, you still got a little open pan there that you have to chemically treat, or a coolant tire chemically treat. Low operating costs, we talked about the EERs being somewhere in the middle of a air-cooled split system versus a water-cooled central system. Energy availability, meaning that you could use gas for your heat absorption or electric heat, or actually heating water. And I've seen actually some applications where you had a water source heat pump system tied on to a central heating water system where they might run heating water through a heat exchanger for your heat absorption. And we'll get to some drawings to show you what the heat absorption and heat rejection is. Efficient space utilization, so heat pumps are a good application where you can put them below the ceiling if you had to, or you can space them out where the load is. When we talk about central air handling units, we generally talk about high pressure duct. When we talk about high pressure duct, we talk about high velocities and high pressures, high operating costs, or high static pressures on our fans. So you're paying to deliver that air from a central location to a zone. With a heat pump, water source heat pump, instead of having 100 VAV boxes, I may have 100 heat pumps. So the heat pump is out in the space. So my fan is generally sized for 1/2 to 3/4 of an inch static pressure. In a central system, that fan was sized for 4 to 6 inches of static pressure. I have to generate that horsepower and use that horsepower to get the air delivered in the duct to the VAV box. So there's an inherent savings in using incremental equipment out into space and locating it near the space that don't have nearly as much fan energy. Year-round heating, cooling, it's not a 2-pipe system. Any unit can be heating or cooling. And the ideal application of a water source heat pump system is a large building with lots of exterior space and lots of interior spaces. For instance, when you have this heating loop, and we'll get to this drawing, if you're cooling, you're rejecting your compressor heat to your water loop. If I'm in the heating mode, I'm actually absorbing heat out of that water loop. So if I actually have simultaneous heating and cooling in a building, that's actually the most efficient way to operate a water source heat pump system. Then my auxiliary equipment that is intended to either reject that heat or add heat to the loop is not operating because I've got some units cooling and some units heating. Low installed costs, generally the entire water piping can be run in PVC. For a water source application, your operating temperature ranges are generally about 60 to 100 degrees on your water loop, so there's no need to insulate that pipe. There might be some consideration for insulating in a geothermal system, even though I don't see it happening in the field. Most people are using high-density polyethylene piping and not insulating their pipe. But you, like I said, you can operate down to as low as 30, 35, 39 degrees if your loop is not functioning properly. Accessibility to the equipment, drain pans, filters, and compressors. You know, you got one access door on the front of the unit that gets you to everything on these units versus climbing in an air handling unit. Noise considerations, generally you can get compressor blankets on water source heat pumps to reduce your compressor noise. Most manufacturers of these compressors, these little scroll compressors and recip compressors are putting in these units nowadays, they just don't make noise. So you don't generally have the problems that you might have had 10 or 15 years ago with horizontal units that are above the ceiling where you had to consider noise. Freeze protection. You do want to consider freeze protection in a geothermal system. Again, you've got a loop that's going through a heat exchanger in this heat pump. It's a refrigerant to water heat exchanger. As I mentioned, you can get very low condensing water temperatures. So most manufacturers offer freeze protection on the outlet of your or inlet of your heat exchanger that would actually just shut the unit down and prevent freezing of your heat exchanger.
Is that an option line?
It's an option on any manufacturer. Scheduling on-off times, like I said, you could add controls to these things and do anything you want to as far as scheduling them on and off, night periods, unoccupied periods. They're pretty easy to commission. Like I said, it's just a simple piece of equipment. It's a compressor and a fan, 5-wire thermostat, or you can put a controller similar to a VV box controller on it to tie it into a front-end control system. What you have in the loop, let me go ahead and get to, in a water source heat pump system, you're going to have a piping loop similar to most any other piping loop system, where I've got heat pumps, I've got a circulating pump, circulates water out to the heat pumps, turns it back to a boiler or a coolant tower. And I've got some drawings that show that. But you will have a circulating pump in the system just like any other chill water or heating water system. Most any kind of pump works. Again, you can add a solenoid valve on that heat pump, whereas when your tire water or loop water is in your heat pump, I can put a 2-position valve and just connect that valve to the compressor relay. So whenever the compressor is off, the valve is closed, and I can actually incorporate a variable volume or variable water flow system into my heat pump loop. Boilers are used for the heat of absorption. I'll show you how we implement the boiler, but any kind of boiler we use, gas, propane, electric, copper tube, steel tube, condensing. Probably the best application is that condensing boiler that we can operate down at very low water temperatures. If we don't use a condensing boiler, you have to be very concerned of how you connect your piping up to the boiler, because again, any water temperature less than 140 degrees in that boiler is going to cause sweating unless it's a condensing boiler. But there are ways to get around that. What to do, they just bypass some of the supply water to the return water and bump the return water temperature up. And you'll see in the drawing, the boiler is a sidearm application of your loop system. You don't run all your water flow through the boiler. That's just not necessary. So normally you just take a little water off the loop, heat it up, and inject it back into the loop at a very high temperature, mixes with your loop temperature to maintain whatever loop temperature you're going to try to maintain. Water conditions, there would be a minimum flow if you had a variable volume application, you want to try to maintain a minimum flow for your pumps and whatever your pumps can turn down to. You're normally controlling your return water temperature to the heater's rejection equipment. Condensate drains off the heat pump just like any others. Minimum flow through a boiler. I guess we're talking about boilers. Most boilers are going to have a minimum flow with the exception of that condensing water type. So you have to look at how you're piping that up. Return water temperature we talk about, you have to be concerned in non-condensing water temperature boilers. In any condensing water temperature, or in condensing boiler, you've got the condensate drain coming off the boiler that's kind of acidic. Sometimes you have to run your condensate drain off your condensing boilers through a neutralizer. Flues, standard boilers, you know, we talked about that the other day, type B. The condensing boilers, some of them are the AL 294C stainless. Some of them actually use PVC because your condensing temperatures are so low and your efficiency is so high that your boiler temperature is generally less than 110 degrees coming off the boiler, where in a standard water tube boiler might be 350 degrees. Heat rejection. So the cooling, if ever all the units are cooling, we've got to come up with some type of heat rejection method, and that's a closed circuit fluid cooler. The closed circuit fluid cooler is what I guess you'd say the standard in the industry. There is one drawback to that. So I've got a big, huge heat exchanger right here. I've got a fan, centrifugal fan, that is blowing air through the coil, and this is a big heat exchanger. It's an air-cooled device, even though you can operate a spray pump and a spray system with it to get your water temperature closer to that wet bulb temperature. But this is a $20,000 coil that I'm going to set outside, half-inch or 3/4 inch tubes. So there's my return water going in, or my supply water coming out, and my return water going in. I've got to add glycol to this system because this is sitting outside. Whenever I add glycol, that increases my pump energy, decreases my heat transfer on my coils, reduces your energy efficiency just a little bit. But in a fluid cooler, where I've just got just this steel or copper heat exchanger with air going across it, that's one way of getting heat rejection out. The other methods are standard cooling tires. One application is a heat exchanger where my heat pump loop is going this side, my tower is going on this side, and I'm taking water out of a standard cooling tire, putting it back in. This pump and this cooling tower only run in your heat rejection mode, which is the summertime mode. This is inside your building. So this is a standard cooling tower, an open loop system that you might put a basin heater in here, or you might actually just shut it down and drain it. So some type of fluid coolers or heat exchangers and cooling tires. Some people have added cooling tires to heat pump loops, but these heat exchangers inside the heat pump, very small tubes, 1/4 inch tubes. You want to try to keep the water as clean as possible, so it's not a good idea to add an open cooling tire to the heat pump loop, because you will get trash in that water. Closed circuit fluid coolers, again, they might have a spray pump. They got coils we talked about, copper, galvanized, discharge dampers to hold some of the heat in when it's off, fans, and if you do have water treatment, if you do have that spray system with a basin heater. Open cooling tires, we talked about that. Generally, you would want to heat that heat exchanger with an open cooling tire. Hydronic accessories, just like we talked about the piping loop systems, you're going to have an air separator, you're going to have a backflow preventer for makeup water. It pipes up just like a chill water or heating water system. Yes, sir?
There's nothing on the screen.
Regulating water systems, we talked about how you size that bypass valve. You can do, in a glycol system, if you do have glycol in your system, and lots of water source heat pump systems, especially geothermal systems, have glycol. You've got that, your circulating water pump, and you've got your line, you've got your relief valve. And we talked about that makeup valve. You know, the size for the height of the building. Well, in a glycol system, you don't really want a direct connection. So in a glycol system, there's little package systems that maintain your glycol in a tank. And then you have a feeder pump in the glycol that actually feeds into your system. And this would go away. So this generally would have to go at the top of your building because you can't generate any static pressure. So when you have glycol, and you do have an automatic feed, and you can do it like this, but you don't have anything to make up that minimum static pressure in your system. So this would go at the top of the building. But you can put a backflow preventer on a glycol system and have a direct connection. Most people don't. And then this relief valve here actually drains into the tank.
Is that very common?
It's expensive, so I'd say no.
Okay. I mean, I haven't seen one.
Yeah. The alternative is you just lose your glycol if you leave water.
We just put one in out there, but
Yeah. What building was that?
weapon
Yeah.
simulator.
Sold by Jacob Sims. I guess there's no more than a couple manufacturers, but there is a way to maintain your glycol and not lose glycol when you release water.
Just a second, how was it? You said it's not actually connected up to it, to your water source?
No, your water source would be just an open valve that you would fill your system up with.
Okay.
And then you would have a glycol tank and a feed pump that operates on a pressure switch right here. So whenever you lose pressure, whenever you relieve water, the glycol is pre-mixed water.
Oh, okay.
So it's water and glycol, pre-mixed in whatever solution that you want, 20%.
So it's metered into your water system?
Yeah, this pump is metering it in based on the pressure.
Okay, so it's just not all mixed together and,
Right.
okay, I got you.
That's how most systems work.
But in theory, once you get your glycol in there, you know, it's pretty good.
Well, some people have leaks. Especially in geothermal systems.
No.
When you have a plumber
I
involved,
see a lot of geothermal come in and have makeup water.
Well, generally, they'll have an open tank that may be stacked up high. just
Well,
adding
I saw one
static
of those at
pressure.
UALR,
Yeah, over in the house.
yeah. Yeah.
You know, it is a closed water system, so you would have to have an expansion tank and a relief valve. We talked about the deadhead plus static head of your pumps, how to size that. We're going to review those things again. Controlling the system, there's scheduling, you can do variable volume applications, we talked about that. I want to get into the drawing. We'll come back to some of this. Let's talk about the boiler. The boiler is to add heat in the system when the heat of rejection is less than the heat of absorption. We talked about simultaneous heating and cooling. So if all the units, or the majority of the units are heating, they're actually absorbing heat out of your loop temperature is dropping. So I gotta have a boiler to supplement that loop temperature and raise it back up to my set point, which in the wintertime in water source heat pumps is generally about 60 degrees. Size of boilers, you can determine your heat loss, take the sum of the heating output of all your units, take that output in your heating loss, and you come up with a diversity. And there's a little formula right there at the bottom. Output divided by building loss times heat of absorption divided by your boiler efficiency is your boiler size. So, point being that your heat pump boiler is not sized for your total heating loop of the building. You can take some diversity. You can take credit for units being oversized. So there's a method to just come up with a small boiler. Matter of fact, we have a little boiler in our building that's only about 100,000 BTUs. Heats this whole building because we're depending on the compressor heat, actually being rejected to the loop, or enough absorption loop in the wintertime that we've got some simultaneous heating and cooling going on in the building. The fluid cooler selection, again, the purpose of the fluid cooler is to reject the heat during the loop. The cooling mode, all my compressors are on, I'm rejecting heat to that water loop, so my water temperature is going up in the building. So I've got to have a means and method to reduce or reject the heat from the building. Again, there's ways to size that fluid cooler. Pump selection is just like any other building. We take your total flow, take your maximum diversity times the heat pump flows equal to heat pump flow. So again, you don't necessarily have to take your connected load of all these units. You can consider diversity in some design methods. Take the pressure drop of the system, plus any load that you've got on, say, your valves or solenoids, that's going to add pressure to your system. Fluid cooler pressure drop, and the piping system losses. Develop your total head and size your pump. We're going to talk about that next week. Geothermal applications. Loop fields. You can have series and parallel loops. Most people, the loop field is, again, it's just another place to reject heat or absorb heat. When you come outside of the building, generally most people come in and they'll drill holes in the ground, they'll come back. These are called parallel loops. So all these loops are parallel. They come off the supply, they go right back into the return into your building. And the intent is, in the summertime, you're coming out here at 100 degrees and you're hoping to go back at 90 degrees, using the ground as a heat exchanger. In the wintertime, you're coming out here at probably 50 degrees and you're hoping to come back at maybe 60 degrees, an ideal loop. It gets colder than that if your loop's not working in the wintertime. There are series loops where some of these you might have a loop like this. That would be 2 series loops. Again, it depends on what your pipe size is. And most of these loops are 3/4 of an inch. Vertical piping. Horizontal is whatever it takes to get all your loops together. Some of these series loops, you got to be careful about how many you put in series, again, because most of this is 3/4 of 1 inch piping.
Do you get water down there?
Well,
Is that a plus or not?
plus is, hitting water. So this is your well. They drill a 6-inch well, and this is a packaged roll of pipe with a typical, very close coupled U-bend connector on the bottom of it. They push your pipe down there with grout, and the grout is very important because it is your heat exchanger back to the ground. So there's a special type of grout they use, bentonite or some other type of driller's mud that they use for grout that uses the heat exchanger. And so generally it's a 4 to 6-inch well that's being drilled 250 to 500 foot deep.
Do they always hit water or they just open it up?
No, what you normally do is in a test well, or if you're going to do a geothermal application, you come out and drill 1 or 2 wells. And they test the ground. They actually heat the water up, put it in the ground, and put it back up to have a heat source. And they're testing the conductivity of the ground to see what kind of heat rejection or heat absorption they can get out of the ground. The ideal ground is rocky with water flow through it. If it's a rock ground, water flow going through it, you have an incredibly good heat exchanger. Incredibly good heat exchanger. If there's no water flow through the ground and it's purely sand or dirt, then there's really no heat exchange. I mean, you're going to get what's called I can't remember the terminology, but you're just heating the ground up. And eventually your loop goes bad.
Pretty like a dead air pipe then.
Yeah. So ideally, you get high conductivity when you have water flowing through the ground.
What about putting it in the lake, Steve?
There are applications where you can buy stainless steel heat exchangers and put them in the lake, or you can actually drop these pipes into a lake. There are other applications called slinkies. What you have to do is you build actually a jig, maybe out of 2x4s or 2x6s, and the designer tells you to take a piece of 3/4 inch or 1 inch tubing and start coiling it like this. And you'll get a specification that says what that dimension has to be and what this dimension has to be. And you just wire tie the pipe together. That's called a slinky. Generally, they'll run up to 500 foot in length.
Whoa.
Right down in Texas, Colorado River, they actually had where the pipe went down into the river itself, had to have a screen on the end, to keep the trash out. But in fact, that was one of the problems of the airflow or the water flow. Every now and then, that screen would fill in.
Yeah. Now, the third method, this is generally in a horizontal ditch. So I've got a ditch that's generally 5 foot deep to 7 foot deep. And this slinky is laying in that ditch. This is vertical well application as well as horizontal well application. I can dig the same ditch and put my supply and return pipe in it in the horizontal application. Generally, your piping lengths might be 60% more in a horizontal application because, again, you're not getting quite the conductivity as in a vertical well. This can be in a horizontal ditch. It can be laid in the bottom of a pond. The other method for geothermal is a supply and return well. It goes into my heat pump. That's a pump down in a well. And you reject it back to another well. That's an open loop system. So you got to have a heat exchanger that's capable of the corrosion that's going to be caused by that open loop system. And they do, and most manufacturers do make a special heat exchanger for what's called open loop systems. But this is your supply well, might be 250 foot deep. You're getting down to a water table, and you're actually supplying water just like your domestic water well at your rural house. But then you got to put that water back in the ground someplace.
What would be the advantage or disadvantage of that particular system?
Constant 50-degree water.
Water and cold water.
Okay.
25 EER in the summertime. So this is what I have in my house. And my return well is my septic tank. Because I don't have any kids at home anymore. Nobody's showering 6 times a day. So I got an adequately sized leaching field that can take that much water and put it back in the ground.
Question. So you're actually, that system right there, I see what you're saying, that pump is actually pumping water from the
Yeah,
ground
this is
itself.
just a typical well submersible pump.
Okay, and then, all right, that's applied there. Okay. now-
And I'm just taking the groundwater and running it through my heat exchanger, and I'm putting it back into a well or some method to get it back into
Okay.
So when your unit calls for heating or cooling, that energizes that pump?
Yeah. Yeah, well, actually, I got a pressure tank here that is a pressure switch, maintains a certain pressure.
So when your valve opens to your heat exchanger,
I got
the pressure
pressure.
valve pump starts.
Yeah, so the
Okay.
pressure switch starts the pump.
What pressure do you run that at?
I can just, it's typical domestic water, 50 pounds.
Okay. So you actually run it that high?
Yeah, it wouldn't have to be that high.
Okay.
Steve, you see a lot of that in commercial applications?
Not in commercial applications, just because of the demand and how you get the water back in the ground. And you couldn't apply that commercial. Those are 3 types of geothermal loops: horizontal well, the vertical wells, slinky pipes, pond water. And like I said, there are people out there making heat exchangers to drop in ponds as well.
Numbers and drawbacks to the algae, things like that.
Well, the algae not so much, but the mussels.
Well, I knew that happened down on the river.
Yeah. there are some applications here in Little Rock that had problems with mussels covering up all the pipe. You don't get any heat exchange anymore.
Is there a problem with heating your pond though? In the
Well,
summertime?
They say in a pond that you ought to have at least 7 foot depth and so many acres per ton.
Okay.
And so there are design methods to use for ponds. But, I mean, if you're gonna do a pond in a commercial application, it'd have to be pretty large. I forget the, how many acres per ton. But, so they had series and parallel loops, vertical, horizontal, the coiled are the slinky. And the loop field conductivity determines your amount of loop. Right, the standard rule of thumb for a vertical well is 250 feet per ton. That's a rule of thumb. It can get worse or it can get better based on your conductivity. And the only drawback to this geothermal system is I might do a conductivity test today. 5 years from now, my water's been rediverted by something that's happened either geologically or construction or something like that. So there's some safety factor that you want to put in that. That goes up to about 375 to 500 feet per ton for horizontal in those 5 foot deep ditches. And in the pond applications, you just have to look at every one and apply.
But now, on your horizontal there, did you have pretty bad summer, don't that hurt you, like the drought?
Well, again, it depends on how much water you got, but that's why they do more horizontal, because you know you're gonna have less water. So you're just extending that heat exchanger area out to compensate for that.
And I think that horizontal is what they mainly use in this area.
Combination of both. We tested our site here for a vertical well, but it was all sand and the well kept collapsing. So it's been very expensive to do it. So we attempted geothermal here, but weren't able to do it. Pumping systems, you know, we talked about the central pumping systems. You can also have that loop. A lot of people, especially in geothermal loops, you got a series of heat pumps. They'll put the little individual pumps on each heat pump. They might actually go to a well and right back into the building. Generally, that's about the only time you put the individual heat pumps on the units. It's when you've got an individual little drop in a geothermal application. Most water source heat pumps, you're going to use a central pump. Again, because these little bitty 2, 3, 4 gallon a minute pumps are 60% efficient. Bigger pumps get up to 80% efficient. It's like heat pumps for lowering water temperatures. Let's go ahead and stop here. And Thursday we'll get into some of the pipe